Okay. Hi, everyone. My name is Max. I'm a co-founder of Arcane Finance, a privacy-centric DEX on Aleo, AMM DEX. And well, today I'll share my experience about building AMM DEX on Aleo. And yeah, by the end of this workshop, you guys will be able to build your simple AMM, like figure out how to write a code in Leo programming language and how to think about privacy. Yeah, so again, Arcane Finance is a fully private, decentralized exchange on Aleo blockchain, the central DEX. Okay, so let's start from discussing like trading in general, how it works. So the most widely used model outside of like crypto and blockchain is centralized limit order book, yeah, CLOB. Yeah, so you probably saw it like a million times on any exchange. So you have like buy orders, sell orders, and there is a trading engine that does order matching. Yeah, but so then blockchains appeared, and people, of course, started like trying to move the same trading experience on chain, and it turned out it was not viable, not usable solution because of scalability, latency, and cost issues. It was the case for Ethereum back then. So currently there are a lot of like alternative blockchains that try to address this issue, kind of being fast, cheap, and so on. But anyway, all of that led to automated market making, AMM exchanges. So the principle is very different from centralized limit order books. So liquidity is provided into pools, and the price is calculated according to a formula. Yeah, and arbitrageurs are responsible for keeping asset prices in line with other markets. So they go, yeah, to AMM exchanges and do trades to move the price where it should be, essentially. Yeah, so this slide like shows the idea behind constant product AMMs, which is kind of the most simple version of an AMM. Think of like Uniswap V2 was one of the first protocol, and of course the most widely used protocol that implemented this model. So basically you have a curve, and the price moves by this curve, essentially. So it's called constant product AMM because the product between the balance of token number 1 and token number 2 remains the same, essentially. Yeah, so here we can see that so the price was at old position, but then trade happened and it moved to another point. Yeah, there are like more complicated versions of AMM, like stable swap, which is a good fit for like either swapping stable coins when their price is essentially the same almost always. And for example, another example is wrapped assets. So think of ETH to wrapped ETH, or for example, staked tokens like ETH or ETH staked with Lido, for example. Yeah, so it has slightly different invariant, and it's in purple and on this slide. Yeah, so now getting to privacy. Okay, so our goal is to build an AMM that would be private, and by private I mean full anonymity, as opposed to pseudonymity, where like yeah, everything is private until user's address is associated with their identity. And in fully anonymous blockchains like Aleo, what we are trying to achieve is to make it absolutely private, so you cannot link different transactions done by a single user and even identify the user's address. So this is the goal of basically of the workshop. So our goals do not reveal trader's address and do not reveal a liquidity provider's address. As well, there are basically like three main functions of the AMM. So you can add liquidity to the pool, then you can do swaps using this liquidity, swap one token into another token, and well, then you can remove your liquidity. And to achieve that, we will use records, Aleo records, to represent tokens. And we'll use mappings to store balances, LP balances, and total supply. Okay, so as this is like a practical workshop, so I suggest that you open your laptop because, well, it will be just probably more interesting to follow like what's going on yourself. So. We'll be using online playground, so it's super easy. You don't have to download anything. Just okay, so it's play.leo/lang.org. Okay, so give me a second. So I'll give you like a minute to open the playground. Yeah, and by the way, there are some rewards for the best result of this workshop that will be granted by Aleo. So kind of, well, it's up to you whether you're interested or not. I think it includes some like sponsorship for trip to one of the Aleo events in Canada, as far as I'm concerned. Okay. For sure. Thanks for pointing out. Actually, you will have an empty. Okay, actually, I can start from scratch. Okay. Now it remembers. I renamed the program. By default, it will be called something like Hello World something, and will contain some code, Hello World-ish code that we are not interested in. So let's rename our program to, let's say, AMM.Aleo. And as correctly noted, we also have to update a program JSON file below here so that it matches. So now we have this program, and now let's think what we can do. I mean, ideally, I would like to do like several iterations on this AMM program, like starting with like the most basic, like straightforward rewriting of Uniswap version, and then like trying to make it more and more private. So let's start with defining tokens. Okay, so we use Aleo records to represent them. So we have token 1. So each Aleo record must have owner field. So it's owner address and I'm pretty sure it is possible, if you can help me with that.
It might work like just a command.
Okay, so you are saying just in, okay, got it. I think it should be possible to do something on HDMI level too, but okay. Does it work now? Okay, cool, yeah, just zooming in, good old zooming in worked well. This is a simple, we'll try to keep it really as simple as possible for this workshop. Okay, so, and we have an amount, and we have another record, token 2. So thinking like token 1 could be something like USDC, and token 2 something like, I don't know, BTC, wrapped BTC, or something like that, okay? And we have the same structure for the second record. Okay, so and here we can create transitions for adding liquidity. Okay, so token 1 and token 2. Okay, so we'll be adding liquidity. We'll be removing liquidity. So here we'll have to provide the amounts. Oh, sure, yeah. By the way, feel free to ask questions.
Can you use the same record for token 1 and token 2?
Do you mean the same type of the record? Well, yeah, we could theoretically have like a token that has also kind of ID field, like token ID field, and you could use like a single type of the record to represent multiple tokens, for example. So it would be something like that, like token ID, and you would have like 1, 2, 3, 4, 5, like, yeah, we'll be able to represent multiple tokens.
When we put it this way, where goes the ID then?
Sorry?
If you put it this way, we don't need to use the ID.
Yeah. So here you distinguish by record type, essentially, yeah. So these are different record types here. Okay, so we'll use, yeah. Oh, sorry, I wrote amount and amount 2. Yeah, and this would return token 1 and token 2, yeah. So in Aleo, yeah, records can only be consumed once, so we won't need like checking user balance or anything like that. So we know if kind of system accepted token 1 and token 2 as arguments, well, it means that they are kind of, they belong to user, and user only token owner. So an owner is represented by owner field. Only token owner can spend it. Only record owner can spend it. And by spending, I mean just pass it to some transition. Okay, and we'll have a transition swap with amount 1. Okay, so let's say we're a swap to 2. Okay, so this means we have token 1 as an input, and we specify the desired amount of token 2 to receive. And now I will elaborate a little on this design decision. So why we are doing it like this a little later, yeah, when we go closer to the actual AMM logic. Okay, so what else do we need? Okay, so when we are adding liquidity, we have to update basically the reserves that we have. It's mapping called reserves. So currently in Leo language, the only field type supported on the top level is mapping. So yeah, that's why we represent reserves as mapping from, okay, so let's say U8 to U1 to 8. Okay, so it means that 1 is token 1 balance and 2 token 2 balance. Probably yeah, not balance but reserve, not to confuse. Yeah. Oh, reserve. Okay, and what else do we need? Well, we need to remember how much liquidity each user provided. This means we need balances. Yeah, so here we can use, in the very first iteration, we'll use user's address. So here we can see, though, like, I probably haven't mentioned that. So all the inputs of transitions are private by default, right? And this means that like when someone will open Explorer, Transaction Explorer, Block Explorer, they won't be able to see token 1 and token 2 in open. They will see just encrypted version of it. Okay, so balances from address to, again, balance, and also we need total supply, which is essentially a single number, but again, right now we can only have mappings on a top level. That's why we also represent it as a mapping. It's always from 0 to total supply of LP. Okay, so each program in Leo has like, each transition has like 2 stages of execution. So the first stage is executed locally, and the second stage is executed on chain. That is called like finalize. So we create the same, essentially, a finalized block with the same name, add liquidity. Okay, so we have amount 1 and amount 2 here. Okay, for simplicity, we'll say that users wants to add liquidity, like the same, exactly the same amount that is stored in record. Because theoretically, user could, let's say he has a record of token 1, like 10 token 1s. So in the amount field, there is number 10. And yeah, theoretically, user could want to spend just, say, 5 token 1s out of 10. But here, for simplicity, we'll consider that user is willing to consume like the whole record. Okay, so we return nothing from this method. Yeah, then finalize. Okay, so here we have to do what? We have to top up user balance and add tokens to reserves and recalculate total supply. Okay, and here actually to top up users balance, we also need address. So we can say address, so someone's address. And here, so we take token 1 owner as someone who's adding liquidity, and also pass token 1 amount and token 2 amount into the program. Okay, yeah, so now let's see how we are working with balances. So we do mapping get or use. This is a common to access mapping, and we are getting yeah, we're working with with balances. Our key is user, and the default value, if it is like not present here, okay. Yeah, okay, there is a typo. Okay, and the result of this call is the balance. Okay, so it's like current balance. Okay. The next step, so we are understood like current user balance. Now we'll need to recalculate this balance using a formula, like constant product formula. Okay, also what we need to do, we need to add tokens to reserves. Okay, so again, we are reading as per our agreement reserves, and the default amount is again this. Okay, it's token 1 balance of type U100, yeah, 28, Okay, so token 1 balance, and oh, sorry, it's not, should be reserves, so why is it complaining? Oh, okay, I mixed the order. Okay, this is token 1 balance, and there is token 2 balance, the same, but we pass 2 instead of 1. Okay, and so now we can update this balance. So updated token 1 balance is like token 1 balance plus amount 1. Okay. And we are doing the same for token 2 essentially. Adding amount 2. Okay, so here now we need to update mapping. So we're setting back this value to the mapping. So we're updating reserves 1U8 with the updated token 1 balance, and do the same for token number 2. Okay. So yeah, this part actually is done, and now we are adding. So we topped. Okay, so we done this part. We added tokens to reserves, and now we have to update user balance and recalculate a total supply. So let's see how it works. So this is like yeah, how constant product formula works. So let me read the current total supply. It's the supply of LP tokens. We are reading from total supply mapping, and there is a single value there because it's essentially a field, but again, we have to use mappings for now. Okay, so we are reading this. Yeah, and the default is again 0. Okay, so this is a current total supply. And now we have to calculate the amount of LP, like liquidity tokens. Okay, we're doing this by, okay, let me check with my notes. Yeah, don't want to screw the math here. Yeah, sorry. Okay. Yeah, okay, so this is removing, this is adding. Okay, yeah, so we multiply the total and divide by reserve. Okay, so we take amount 1 multiplied by current total supply and divide it by reserve number 1, which is okay, which is token 1 balance. Yeah.
There's a type at line 4.
Okay, let me see. Oh yeah, sorry. Auto completion, yeah, works a little weirdly here. Yeah, okay, so we are doing LP1 and LP2, and essentially, yeah, doing the same. And now we have to calculate like what is the minimal of them to add to users' balance. So user is supposed to provide the liquidity in the same proportion as they were, in the same proportion as it is already inside the pool. So, and that's why we are taking the smaller one to give user a proper amount of liquidity. Okay, so here it's essentially a helper function that just, okay, so if, okay, we have turn rate less than B, return A, otherwise B. Yeah, I believe I didn't screw the syntax. Oh, okay. Yeah, I guess it is correct. Okay, and now LP is like the LP is minimum of LP1 and LP2. Okay, so actually this is not transition, sorry. It is an inline, yeah. You cannot call one transition from another transition, and from both from finalize and from transition, you can call inline, which is basically an inline function, okay? Okay, so let's see, yeah, so now what we did, so did we top up users balance? Not yet, okay, so we have our current user balance, and now we have to add to this balance current balance plus LP. Yeah, now we know how much user has. And now we will recalculate total supply. We actually already recalculated it. So we're now updating the mapping by saying set total supply 0, and we are adding LP. Okay, so it was current total supply plus LP. So yeah, actually yeah. So we are more or less done with adding liquidity. Okay, but yeah, here is a problem. So as I mentioned before, user address is like fully public, and well, we want to fix this. Well, the easiest fix, though, like not 100% perfect, but we'll probably start with it, is replacing address with a hash of address. Field is a Leo specific type. That's basically a finite field. You can think of it just like very large number. It's 253 bits. Yeah. Okay. Yeah. So and here instead of passing user's address, we can pass BHP256 hash to field. Yeah. Hopefully this syntax is correct. Okay, that type field was found, yeah. Field, okay. Yeah, as mappings are public and they live on chain, like in a way similar to Ethereum, we can see that, yeah, now at least looking at this mapping, into this mapping of balances, you cannot see like which addresses are there and which are not. But if you know like specific address which you want to check, you can calculate this hash yourself, and yeah, you will be able to find out whether certain user provided liquidity into this pool or not. Well, if we have time, we can do a next iteration to improve this. Okay. So what we got was, okay, so I think removing liquidity isn't like super interesting. Probably swapping is more interesting. Okay, so what we do. Yeah, now user has token 1, and they say they want to get amount 2 tokens. Here, yeah, I need to explain, so why can't we just calculate automatically how much of token 2 user will receive? Because, well, all the data is on chain, and yeah, it's possible to calculate by applying constant product formula. But it is not possible because we want to issue the record in transition, And in transition, you can only you cannot read mappings. You can only read mappings in finalized section when like the transition is finalized on chain. This means we will quote unquote like trust user first when we issue this token in transition, and then in finalized section we will just double check that the amount provided by user does not exceed the amount he should receive according to math. So this is like the pattern that is used pretty often in Aleo, where you like provide some value into transition as an argument, and then you double check this in finalized section whether it was correct. Okay. Cool. Here, we are creating token 2 of type token 2. Okay, and the owner will be token 1 owner, and the amount will be the one that is specified by user. But if finalized section fails, then transition fails too. Yeah. Return token 2, then finalize. Okay, so and we'll provide swap to 2. Yeah, we will provide token 1 amount. Okay, so amount 1, and we will provide amount 2. Okay, amount 2. Yeah, and here we have to like figure out whether it was like correct. So let's see, and increase and decrease balances of reserves. So yeah, let's do a little bit of copy pasting here. Okay, so again, we are reading the reserve of token 1, and as we swapping 1 for 2, so we are increasing. Okay, yeah, actually copy paste worked pretty well. I don't even need to change anything here. Yeah, so we are just adding amount 1, and for the second amount. For the second amount, we have to decrease it as we issued token 2 record. Sorry, here's a mistake. Yeah, as we issued token 2 record, and now our reserves decreased accordingly. Okay, so we updated the reserves, and the kind of the essence of AMM is that this swap did not change our total supply, and it did not change balances of users. So anyone has the same amount of LPs, but they are just represent the assets in different proportion according to the price that was changed. Okay, so here we need to check that the swap was correct. So let's calculate real amount 2 is, okay, let me also kind of double check this, because yeah, might screw the math on the go. Yeah. Okay, so we are checking, okay, basically checking reserve. Okay, yeah, that's really even easier than that, yeah. So we have old reserve, yeah, where we are like using constant product formula very directly here. So what we are saying that token 1 balance multiplied by token 2 balance is less than or equal, yeah, less than, yeah, probably less than our new state, which is updated token 1 balance multiplied by updated token 2 balance. So we are, yeah, very, very directly, very explicitly just checking the constant product equation that x multiplied y is k. Okay, so yeah, this means that if the amount 2 was bigger, larger than it should have been according to formula, the finalize function will fail, and yeah, the swap in general will fail. So the user will not receive this token that was issued in transition, as it won't be finalized, so it won't appear on the blockchain at all.
How do you calculate the amount?
Yeah, so essentially, yeah, so there is a formula how you can do this. So in a way that, so you could derive it from this assert, essentially. So you take, you just use, you can use this assert to kind of figure out how to, what is the maximum amount to that makes this assert not fail, essentially. So you can do this with a paper and and pen. Yeah, just don't have the formula off the top of my head. Yeah, the thing is, so this is as this is an argument of swap to 2, so this is calculated off chain. Yeah, so you calculated this off chain, let's say on your front end. Before you call this this transition, you do this calculation, and then you just on chain you just validate that. Again, you have to do this because in this block in transition you do not have access to mappings, as this code is executed locally, like these values like token 1 and amount, all of them are private and they never leave your machine. Zero knowledge proof is generated that this code was executed and executed correctly, and then yeah, finalization happens, and these parameters are public. So yeah, the external observer will see that this swap indeed happens. So someone is swapping amount 1, certain amount of token 1 into certain amount of token 2, but they won't be able to see who is the owner. So this is kind of the idea of privacy that can be achieved on Aleo. Okay.
Should we move the line 67 to the beginning of the function?
Can I move it? Yeah, but actually it's kind of, it has no impact. Oh, but actually no, I can move it higher because I use these variables that I calculate the updated balance. Yeah. Okay, yeah, so this is an assert that we have. Yeah, so what we can try and do, we can try and think like how we could further improve the security of this program. I mean, like the privacy guarantees. As here, again, as I mentioned before, balances store hash of address to balance, which is kind of not ideal, I'd say, right? Because it means that if I know your address, I can just calculate hash and see whether you provided, how much liquidity you provided into this pool. We can do better than that, okay? So instead of using hashed address, we can use just a random number for that. And we need to have LP token record to represent this ownership. Okay, so this LP, let's call it like, okay, deposit ID field. Okay, so let's see how can we do this. So when adding liquidity we just provide deposit ID, which is again can be generated off-chain, must be generated off-chain, okay, and return this LP token that basically represents the fact of ownership. Okay, so when we used address, we could just, I think I didn't use it anywhere. Actually, you can use self-caller call to kind of get the address of a user who calls this transition. Okay, but here, we are replacing that with an LP token record, which helps us to keep everything private. So LP token. Owner, let's use self-caller here. Anyway, only an owner of these tokens can call the transition with these records, so there is no way to spend other users' records, even though you no nonce, no like not ciphertext, but like open text of these records. You still cannot spend them without a private key. Okay, and deposit ID is deposit ID. Okay. This thing is private. So caller, but caller is stored inside the record, and the record is private. Yeah. Yeah. So this thing is invisible. Yeah, it will be encrypted. It will be a ciphertext in the blockchain. Yeah. So everything dealing with records is private by default. You can add public modifier if you want, but by default everything is private. Yeah.
In this case, there is no necessity to use the user address publicly at all.
Yeah, you just need to specify the owner. Like every record has to have an owner. But we don't pass a caller address or even a hash of a caller address into finalize block. And finalize block is like very similar to like your Ethereum smart contract function. So it's like everything is public there. Okay. So instead of a user, we now just say this is a deposit ID. Okay, and we pass this deposit ID. And so now, what we achieved here, probably there is user somewhere still, we are using deposit ID instead. And now what someone can see, they just see that someone that has a certain record has this much of a balance inside this program. And to kind of get this, to withdraw, to kind of remove your liquidity, you would have to provide this LP token as something. I can actually update the remove liquidity function. So here you specify amount 1 and amount 2, and also you would provide this LP token.
Does the user actually own that LP token?
Sorry?
Blockchain? So as a result of providing liquidity when that thing finalizes, is that caller getting an LP token back?
So what happens again? So LP token is just a record here, right? So, and actually you can see it has no amount inside, because amount, like the actual amount is calculated inside finalize block. So it's basically kind of a receipt that confirms that you were the one who deposited these amounts. So the amounts themselves will be on chain. Your like deposit ID will be on chain, but it will be impossible to link your address, your identity with this deposit. So this is the idea.
And the deposit ID we just pick up ourselves?
Yeah, just randomly, yeah. So, yeah, again, something that in Leo language there is randomness is available only in finalized block.
So there's
Yeah.
a way to map
Mm-hmm.
the user address, but private, right?
Yeah. So it's record. Yeah, it's like not a mapping. Yeah, it's a record that is private. So yeah, and the fact that you own this record, yeah, proves that you kind of can withdraw this deposit. So this is the main idea behind that. Okay, so yeah.
In what way it should be kept offline? Is it just a record? Where do I keep this LP in my wallet?
Yeah. So this is stored like, think of an on-chain, but in an encrypted format. And when you open your wallet, like Leo wallet or Puzzle wallet, it synchronizes the state of your wallet with the network. So there is like synchronization. So it basically reads all the records from the blockchain and like checks them with your view key, and the ones that match your view key are stored in your in the wallet as a local state.
So I don't need to keep those tokens somewhere myself.
Yeah. If you like, I don't know, like delete everything from your computer, they are still stored on chain. Yeah, but in an encrypted format. Like it's. So record is essentially kind of UTXO, or you can think of it as of UTXO with some arbitrary data fields that you can define there. Okay, so maybe there are more questions, because, well, we can basically code. Okay, so I think we can code this part, token one, owner. We can use self-caller and, or yeah, better actually, LP owner. And amount, again, so we use like the same pattern here. So we calculate the amount somewhere off-chain in our front end, and then later in finalize block, we just will make sure that user receives as many tokens as he's supposed to receive according like to his deposits and his LP balance. But here, yeah, in transition block, we are kind of trusting amount one. Okay, something is wrong. Member, okay, no, yeah, it's just amount. Okay, token 2, and we return token 1 and token 2, and then finalize with amount 1 with the LP deposit ID, amount 1 and amount 2. Okay, so again, finalize name must match. Amount, okay, deposit ID field. Amount 1 and amount 2. Okay, yeah, and so here, yeah, actually, I think we're like a little short on time. So I will just briefly like describe what we need to do here. So get our deposit by ID. Then yeah, we'll see like how much LP tokens does yeah, its balances. Yeah, so it's like random number. It's deposit ID to balance. So we'll see how much LP tokens does this deposit ID have. Yeah, essentially, and like recalculate real amount 1 and amount 2 from LP token amount associated with deposit ID. So this is like the idea. So check, and we will write like assert that like real amount 1 is less or equal, no, actually it's more or equal than requested amount 1. Yeah, so this amount 1 and yeah, kind of the same for amount 2 to make sure that the user did not try to receive more tokens than he actually has. Yeah, so this is like, yeah, super easy version of AMM, super simplified. Yeah, in the real world, kind of, we wouldn't be working with tokens defined in our programs. So these tokens would be external, kind of deployed as an external programs, like use the T program, use the C program. Yeah, there is an ERC20 standard in Aleo, which is, well, kind of similar to ERC20. Yeah, and our program would be structured, yeah, in a more difficult manner. So we would import other programs, and yeah, yeah, we probably, again, as token, here token is consumed as a whole. So we could have something like amount 1 representing the real amount that users wants to spend from token 1. Again, so if token 1 is 10 tokens and I only want to spend 5, I would also receive kind of a change of token 1 and token 2. Yeah.
We also need to take
Oops. Okay, hope everything.
decimal point into account, right?
Okay, amazing. Everything is gone. Fantastic. Okay, but yeah, I'm happy I was able to show you everything. This didn't happen like halfway through. Yeah, sorry about that. Sorry? Oh, okay. This is great.
Could you
Yeah,
put-
actually, yeah, I would love to see like who
Could
managed.
you put it to paste bin and share? Yeah.
Yeah, did anyone like manage to follow the code? I mean, and code on the way?
Do you need to take into account the decimals as well?
Yeah. This is one more thing that you would have in a real life. Yeah, so there would be decimals, like again, very similar to your C20. Yeah.
Mhm. Okay.
But actually, decimals do not impact any math. So they only impact the way you display this on the
Yeah.
front end. Yeah.
So I'm still trying to work through how much of this would be on-chain versus off-chain. It seemed like the finalize would be submitted and run on-chain.
Yeah.
And then the
Transition part is run locally on your machine. Yeah.
Okay.
And the way it works, yeah. So all the programs are deployed on chain. So both parts are deployed on chain, but execution of finalized block happens on chain, and the transition part is used to generate keys. So like when you want to execute, say, swap function from the wallet downloads this prover key, which can be like pretty large, they have like 100 megabytes, and executes everything locally and like signs it with a prover key, roughly speaking.
Okay, and that guarantees that that code is what was run?
Yeah,
and
yeah,
the
yeah.
output is?
Yeah. And on-chain execution is checking this zk part, like that your transition was correctly executed locally, and then executing finalized part. Yeah.
So if I were to peer at that transaction that actually appears on-chain,
Yeah.
I would see the caller address.
You wouldn't see a caller address.
Oh, I would see who submitted the transaction.
No, this isn't
No.
visible in. Yeah. So let
Oh, is that
me.
just not a thing in Aleo? Or
Yeah.
Leo?
So let me show you. Okay. Okay. Oh, maybe some other.
Ciphertext that represents the account that was
Yeah, I hope.
transaction?
Yeah, I hope to show. Yeah, the. Okay, not super familiar with this Explorer, but let me try and go. Like, can I go somewhere? just to show you like, yeah, what you can see on chain. Yeah, for example, program owner is public, but let's go to some transfer private to public. Okay, mint private, for example. Yeah, so what you can see here, like IDs, you can see a program ID, function name, and yeah, some cryptographical like data. And you see, so inputs are fully private, ciphertext something something, ciphertext something something. Yeah, so that's how they appear on chain. And yeah, so here is an output.
Interesting.
Yeah, again.
Would a processing node recognize the sending address?
This is a good question. My answer would be no, but yeah, I don't have like super detailed explanation how it works, to be honest. Yeah.
Okay.
Yeah. So, and here we can see, for example, that finalize arguments are public, so they can be seen. So you should take this into account when you are building something on Aleo. Yeah. So that's why we changed the program a little bit to kind of hide address,
Right.
not pass it into finalize block, because again, finalize is the is public public part. So it's essentially for storing like shared state. Yeah, as like real world programs, as we see, still usually required like shared state to be present somewhere. Yeah. Okay. So thank you, everyone. Yeah, just I'll be here, so please feel free to approach me and kind of show what you have. I'm not sure how this like reward thing will work with Aleo, but I guess like leaving your email address would help to get one. Yeah. Okay, thanks a lot.
Cool.